Welcome to the Explainer. Today, we're dissecting the very anatomy of algebraic change to understand exactly how different mathematical relationships are built. If you've ever stared at a dataset or a sweeping graph and thought, what invisible rules are actually driving these numbers? Well, you are in exactly the right place. Let's jump right in. Here is our roadmap for today. We'll be hitting linear, quadratic, and exponential. Not all curves are equal, radicals and inverse operations, inverse variation dynamics, and we'll wrap it all up with a recap and transfer task. Section 1, linear, quadratic, and exponential. Take a look at this table. It's essentially a cheat sheet for finding clues when you're staring down a data set. Notice how we are consistently labeling our domains, ranges, and units. Tracking those inputs and outputs is how the core mechanism reveals itself. Here's the deal. Linear relationships grow by a constant difference, like adding 50 miles for every single hour you drive. Exponential relationships, on the other hand, grow by a constant factor, or ratio. Think of it like money in a bank account multiplying by a set interest rate year after year. And quadratics, they rely on squaring the input, so the rate changes dynamically, kind of like how a straight distance expands into a squared area. Now, here is where it gets really fascinating. The sheer power of placement. Just look at where the variable x lives in each of these algebraic formulas. In a linear model, x is just hanging out as a standard multiplier next to m. But in an exponential model, x gets elevated to the exponent position, which is exactly what drives that explosive multiplication. And then in a quadratic model, x is the base that's being squared. Literally, just shifting where that single input variable sits completely transforms the geometry and the entire trajectory of the graph. It's wild. All right, time for a quick pause checks to test our understanding. I want you to visualize a data table. You've got an initial starting value of 5 on your y-intercept, but here's the catch. For every single unit your domain increases, the output in the range is multiplied by 3. Based on what we just covered, is this a linear, a quadratic, or an exponential relationship? Take a second and lock in your answer. Okay, if you said exponential, you hit the nail right on the head. It is an exponential relationship because our data is growing by an equal factor over equal intervals. That constant multiplier of 3, that's what we call our constant ratio. If this were a linear relationship, we'd be adding a constant difference, like adding 3 each time. But since we are multiplying, we are officially riding an exponential curve. Moving on to section 2, not all curves are equal. So here's a crucial point, and it's a trap a lot of us fall into. When we see a straight line bend on a coordinate plane, our brains immediately want to categorize it. We see that swoop and think, it's a parabola, or, oh, that's definitely exponential. But actually, scratch that. That assumption is mathematically false. Just because a graph curves does not mean it's shooting exponentially to the moon or forming a perfect U-shape. There's a whole bunch of reasons why numbers might curve on a graph. Let's look at the actual evidence. If we compare a quadratic equation, which gives us that classic U-shaped parabola from squared inputs, to an inverse variation curve like the reciprocal toolkit function y equals 1 over x, the difference is stark. Inverse variations create hyperbolas. They aren't curving because something is being squared or because they're growing by a percentage factor. They curve because the variables exist in a reciprocal relationship, multiplying to a constant. It just goes to show, entirely different mathematical anatomies produce entirely different types of curves. Section 3, radicals and inverse operations. Let's see how this actually builds out our algebraic toolkit. Inverse operations are, simply put, the tools we use to solve equations by undoing the original action. Because think about it, you can't isolate a domain input without a way to reverse the math that was done to it in the first place, right? Addition has subtraction, multiplication has division, and squaring? Well, squaring has the square root. This step-by-step process really shows off the beauty of radicals. If you have a quadratic equation, like y equals x squared, the absolutely only way to get x by itself is to apply the square root, the radical, to both sides. This radical equation perfectly undoes the quadratic. It seamlessly connects the algebra we're doing to the geometry of the graph, literally collapsing that squared area right back down into a single, one-dimensional side length. Let's do another pause check to really lock this in. Imagine the area of a physical square is modeled by the quadratic function a equals s squared. How would we use what we just learned about inverse operations to work backward and find the side length s if we know for a fact the total area is exactly 36 square units? The reasoning here is straightforward, but it's super powerful.
you simply apply the radical as your inverse operation to both sides of the equation. The square root of 36 is 6. By undoing the square, we pull that original side length of 6 units right out from the quadratic area. Which brings us to Section 4, Inverse Variation Dynamics.
Okay, it's absolutely crucial to distinguish between a curve that decays exponentially and one that drops because of inverse variation. They look similar at a glance, but they are not the same. An exponential decay curve drops by a constant percentage rate over equal intervals, kind of like a radioactive isotope losing half its mass over time. But an inverse variation curve drops for a totally different reason. Here, the domain and range decrease proportionally because the two quantities are mathematically tethered together. Their product always has to equal a constant total. Let's look at this real-world table to make it a bit more concrete. Imagine you have a fixed driving distance of 100 miles. The time it takes to drive those 100 miles depends entirely on your speed. If your domain is a speed of 25 miles per hour, your range output is 4 hours. But if you double your speed to 50, your time is immediately cut in half to 2 hours. Notice how the speed and time always multiply to exactly 100. As one goes up, the others simply must go down to maintain that balance, and that traces a perfect inverse variation curve. Finally, Section 5, Recap and Transfer Task. All right, let's sum this all up in 3 quick sentences. First, remember that linear functions add equal differences, while exponential functions multiply by equal factors. Second, not every curved graph belongs to the exponential or quadratic families. Inverse variations have their own unique reciprocal dynamics going on. And third, radicals are the mathematical keys that act as inverse operations to expertly undo quadratic equations. I'm going to leave you with a final transfer task to chew on. Consider the return on $10,000 invested at a 4.25% annual rate. Now, contrast that with the time it takes a car to drive 100 miles at speed v. I want you to apply your new structural lens to this scenario. What clues in the data tell you which curve is exponential and which one represents an inverse variation? Think about the underlying mechanics of how those variables actually relate.